Okay, good morning everyone. Today our topic is apparent raising of the bottom of vessel containing water. We're going to do a bit of a derivation here to find the relationship between the refractive index of water and air with the apparent depth and the real depth. So let me start with the diagram. Say this is a vessel, and if this is the depth of the water, this is the level of the water. So we're going to consider a ray of light coming from the bottom of the vessel, PA, and this will go as AC. Now the angle of incidence for this ray coming from the bottom of the vessel is 0. Since the angle of incidence is 0, the ray will not suffer any deviation. So let us consider a ray of light PA with an angle of incidence 0. With an angle of incidence 0. Now, one thing that you should always remember is this is air medium, which is rarer, and this is water medium, which is denser. Now, the ray PA will not suffer any deviation. So, the ray PA will not suffer any deviation and will continue as AC. So it will continue as AC. Now we will consider another ray from the same point, from the bottom, from the point P, with an inclination, and say this is the normal. Now this ray will be refracted. So this is P, B, and say this is D, N dashed. So this is the normal. Now the angle of incidence for this ray PB will be theta W, and the angle of refraction will be theta A. So the direction as well. So now we're going to consider, let us consider another ray PB with an angle of incidence theta W. So this angle is theta W. And the angle of refraction is theta A. This ray will suffer deviation and make an angle of refraction theta A. Now, just looking at the diagram also, you can make out that theta A is greater than theta W, or the angle of refraction is greater than the angle of incidence. That is because the ray of light travels from denser medium to water medium. So here theta A is greater than theta W. Keep that always in mind. So the angle of refraction is greater than angle of incidence. Now we are going to trace the refracted ray backwards. So we're going to trace backwards, and the ray will meet the previous ray PA at Q. So on producing the ray BD backward, it will meet PA at Q. Now this position Q or point Q is the virtual position of the point P, or in other words, the bottom of the vessel is raised to the point Q. It is raised. So this is the virtual bottom of the vessel. So now let us take one of the right angle triangle. So in right, okay, before that let's write the apparent depth and the real depth. So this QA is the apparent depth and PA is the real depth. So again here PA is the real depth and QA is the apparent depth. Now we'll take the right angle triangles. So in right angle triangle AQB. Now in this right angle triangle AQB, this is the right angle. So this angle and this angle AQB will be equal to NBD, which is equal to theta A, because they form corresponding angles between two parallel lines and the transversal. So angle AQB will be equal to angle NBD equal to theta A, since they are corresponding angles. So this angle becomes theta A. Now take the sine of theta A. Sine theta A will be given by the perpendicular, which is AB, and the hypotenuse is QB. Call it equation 1. Then take you can separate this figure for simplicity's sake. So this is A, this is Q, this is B, theta A. Then take the other right angle triangle, which is APB. Now this angle is important. So in right angle triangle APB, angle APB will be equal to, now APB, this is the angle, so it will be equal to PBN dash. This will become theta W because they are alternate angles. P, angle P, B N dash, which is equal to theta W, alternate angles. So take the sine of theta W. Sine theta W equal to AB by PB. Call it equation 2. Now, we're going to take the refractive index, all right? So, refractive index of water with respect to air will be given by nu WA equal to sine theta A by sine theta W. This is according to the second law of refraction, or in other words, Snell's law. So you can refer to the second law of refraction. So sine theta A is given by, in equation 1, AB by QB by sine theta W is AB by PB. So I can cancel this and this. We'll be left with QB by PB. Let's call this equation 3. So now, if you assume A and B comes closer and closer, or at one point, if they are coincidence. So when A and B are very close, you can assume that QA equal to QB, because if this comes closer, so this will become straight, so QA will be equal to QB. And similarly, PA will be equal to PB. So now in equation 3, refractive index of water with respect to air now will become, so instead of QB, we are going to write QA. Then instead of PB, we are going to write PA. So therefore, refractive index of water with respect to air is given by, so this is the apparent depth, and PA is the real depth. So this completes the proof, and this is the point that we're going to make, and a very important question from examination point of view. I hope you will all understand the derivation, and in case you have any question, you may ask me. Okay, thank you.